Now, in this lecture, we'll answer on two questions. In the first question, we'll find out the area of this semicircle that is inside quarter circle AOB. And in the second question, we'll find out the area of this green shape that is inside rectangle ABCD. So we'll start with the first question. In the drawing, we have quarter circle AOB, and inside we know that side AO of this quarter circle is equal to 5 units in its length. That is to say, the radius of this quarter circle is equal to 5 units, and inside this quarter circle AOB we have this semicircle, and our mission is to find out the area of this semicircle. So in the first step, we will define the center of this semicircle. This point is point C. Likewise, we will define the point of tendency. We will define the touching point of this quarter circle with this semicircle. This point is point F. And we will define the second touching point of this quarter circle with this semicircle. This point is point G. We will define the point of tendency of tangent AO with this semicircle. This point is point H. And finally, we will define the point of tendency of tangent BO with this semicircle. This point is point L. In addition, we will define the radius of this semicircle as x. So CF is the radius of this semicircle, that equals to x according to our definition. CG is also the radius of this semicircle, that equals to x. In the next step, we join point C and L together by a straight line. CL is of course the radius of this semicircle, that is equal to x. We will join points C and H together by a straight line. CH is also the radius of this semicircle, that is equal to x. So here we can implement rule 1, because we have the radius CL that is equal to x. The radius CL of this semicircle is drawn to point L, that is the point of tendency of tangent BO with this semicircle. And whenever your radius is drawn to the point of tendency, then tangent BO will be perpendicular to the radius LC. If BO is perpendicular to LC, it means that this angle equals to 90 degrees, and this angle also equals to 90 degrees according to rule 1. Likewise, we have the radius CH that is equal to x. The radius CH of this semicircle is drawn to point H, that is the point of tendency of tangent AO with this semicircle. Whenever your radius is drawn to the point of tendency, then tangent AO will be perpendicular to the radius HC. If AO is perpendicular to HC, it means that this angle equals to 90 degrees, and this angle also equals to 90 degrees according to the same rule, rule 1. So by doing these constructions, actually created here quadrilateral CHOL. Inside this quadrilateral CHOL, we have 1, 2, 3 right angles. The sum of 3 right angles is 270 degrees. So 270 degrees plus the size of this opposite angle. In total, they must be equal to 360 degrees. according to the rule that states that the sum of the angles in any quadrilateral is equal to 360 degrees. Therefore, this 4 pieces angle must be equal to 90 degrees in its sides. So inside quadrilateral CHOL we have 4 right angles. And according to rule 5, any quadrilateral that has 4 right angles must be at least a rectangle if not a square. So we will relate to quadrilateral CHOL as rectangle because it has 4 right angles. But we also know that the opposite sides of a rectangle are equal to each other. So in rectangle CHOL, side CH must be equal to the opposite side OL. But CH is x, therefore OL must be also equal to x. Likewise, according to the same rule, in the same rectangle CHOL, side CL must be equal to the opposite side OH. But CL is x, therefore OH must be also equal to x. So actually found out that quadrilateral CHOL is not a rectangle but a square because of the fact that all of its sides are equal to each other. All the sides of this square CHOL are equal to x. Each side is equal to x units in its length. In the next step, we will join points O and C together by a straight line. By joining points O and C, we actually created here the right and associated triangle, triangle CLO. So in the next step, I'll copy the right and associated triangle CLO, this triangle in a new page, and we'll implement the Pythagoras theorem in this right and associated triangle CLO. According to the Pythagoras theorem, in any right triangle, the square of the hypotenuse equals to the sum of the sides of the perpendiculars. Here by PT is the abbreviation for Pythagoras theorem. So actually, this is the right and associated triangle, triangle CLO, that I copied from the original drawing. According to the Pythagoras theorem, in this right triangle CLO, CO squared, that is the square of the hypotenuse, equals to CL squared plus LO squared. So I write it down. CO squared, that is the square of the hypotenuse of the right triangle CLO, is equals to CL squared plus LO squared. CO is the missing side, so we leave it as it is. So CO squared equals to CL squared. CL is x, therefore CL squared is x squared plus LO squared. LO also equals to x, therefore LO squared equals to x squared. So in total CO squared equals to x squared plus x squared, that is 2x squared. So I should found out that CO squared equals to 2x squared. Here we take a root out of this equation and finally we get that CO is equals to the square root of 2 times x units in its length. Therefore now CO equals to the square root of 2 times x units in its length. Yes, CO equals to the square root of 2 times x units in its length. So point O is the center of the quarter circle. So from point O, that is the center of the quarter circle, we have here line segment OC, bisect chord FG. Why line segment OC bisect chord FG? Because of the fact that line segment OC divides chord FG into two halves. Each half equals to x. CF equals to x and CG equals to x. So line segment OC that is drawn from point O, that is the center of the quarter circle, bisects chord FG. And therefore we can implement here rule 7. So I'll fix quickly on rule 7. According to rule 7, if a line segment that is drawn from the center of the circle bisects the chord, then the line segment is also perpendicular to that chord. So we have here a circle, and this is point O, that is the center of the circle. So from the center of the circle, that is to say from this point O, we have here line segment OM that bisects chord AB. That is to say MA equals to MB. And therefore, whenever you have a line segment that is drawn from the center of the circle and bisects the chord, like in this drawing, then line segment OM will be also perpendicular to AB. So if OM is perpendicular to chord AB, it means that this angle equals to 90 degrees and this angle also equals to 90 degrees according to this rule, rule 7. So I repeat again, whenever a line segment that is drawn from the center of the circle bisects a chord, then that line segment will be also perpendicular to that chord. So can I actually implement rule 7 in our drawing? Why? Because in our drawing, from the center of the quarter circle, that is to say from point O, we have here line segment OC that bisects chord FG. And therefore, so all the requirements of rule 7 are satisfied, and therefore according to rule 7, line segment OC will be also perpendicular to chord FG. If OC is perpendicular to FG, it means that this angle equals to 90 degrees, and this angle also equals to 90 degrees. So in the next step, we will join points O and F together by straight line. We know that the radius of this quarter circle is equal to 5 units in itself, because OA equals to 5. So what is the definition of line segment OF? Line segment OF starts from point O, that is the center of the quarter circle, and that's in point F, that is the point of the quarter circle itself. So this is exactly the definition of a radius. Therefore, OF is the radius of this quarter circle, that is equal to 5 units in its length. So in the next step, I'll copy the right and green triangle CFO in a new page, and we'll implement the Pythagoras theorem on this green and white triangle CFO. Here by PT is a version for Pythagoras theorem. So actually, this is the right and green triangle CFO that I got from the original drawing. according to the Pythagoras theorem, in this right triangle CFO, FO squared, that is the square of the hypotenuse, equals to FC squared plus CO squared. Again, FO squared equals to FC squared plus CO squared. So I write it down. FO squared, that is the square of the hypotenuse, equals to FC squared plus CO squared. FO, the hypotenuse FO is 5, therefore FO squared is 5 squared, that is 25. And it is equals to FC squared. FC is x, therefore FC squared is x squared. Plus CO squared. CO is equals to the square root of 2 times x, and therefore CO squared is 2x squared. So we found out that 25 equals to x squared plus 2x squared. X squared plus 2x squared is 3x squared. In conclusion, we found out that 25 equals to 3x squared. Here we divide this equation by 3 and finally we get that x squared equals to 25 over 3. Our mission is to find out the area of this semicircle. So what is the area of the semicircle? We actually know that the radius of this semicircle is x, therefore the area of this semicircle must be equal to pi x squared over 2. So I write it down. The area of the semicircle, the area that we are looking for in this question, is equal to pi times x squared over 2. So it is pi over 2 times x squared. And we just right now found out that x squared equals to 25 over 3, therefore we substitute x squared in this equation by 25 over 3. And we do it now and we get that x squared is 25 over 3. So in total, the area on the semicircle equals to, in the numerator of this expression we have 25 pi, and in the denominator we have 2 times 3, that is 6. Times pi, of course. So in conclusion, what we found out that the area of this semicircle is equal to either 25 pi over 6 square units. In terms of numbers, the area of the semicircle is equal to 13.09 square units. So repeat again, we found out that the area of this semicircle equals to either 25 pi over 6 square units, or in terms of numbers, the area of this semicircle equals to 13.09 square units. So we finished with the first question. In the next step, I present you the second question and we'll solve it. Our mission in the second question is to find out the area of this green shape. So in the drawing we have rectangle ABCD. We know that side AB of this rectangle ABCD equals to 5 units in its length. In addition, inside this rectangle we have this semicircle and this quarter circle PBC. Repeat again that our mission is to find out the area of this green shape. So first of all, we will define the radius of this quarter circle PBC, as x. So BC, that is the radius of this quarter circle, is equal to x according to our definition. We know that all the angles inside any rectangle are right angles, and therefore this angle is equal to 90 degrees in its size. In addition, we know that the opposite sides of a rectangle are equal to each other. So in rectangle ABCD, side AB must be equal to the opposite side DC. But AB is 5, therefore DC must be also equal to 5 units in its length. So I write down DC equals to 5 units. According to the same rule that says that the opposite sides of a rectangle are equal to each other, in rectangle ABCD, side AD must be equal to the opposite side BC. But BC equals to x, therefore AD must be also equal to x. AD is one side of rectangle ABCD, but AD is also the diameter of this semicircle. Okay, AD is also the diameter of this semicircle. We will define the center of this semicircle, this point, as point O. So we know that the diameter of this semicircle equals to x. If the diameter equals to x, the radius must be equal to half of it. That is to say, the radius OA of this semicircle equals to x over 2 units in its length. And the radius OD is also equals to x over 2 units in its length. So, in the drawing, we have an external notch between this semicircle and this quarter circle. That is to say, the semicircle touches the quarter circle externally at this point. We define the touching point, this point, as point S. And whenever you have an external notch between two circles or semicircles or quarter circles, you can implement rule 10. So I'll repeat quickly on rule 10. According to rule 10, if two circles touch each other externally, then the side line that connects their centers together must pass through their touching point. So in the drawing we have two circles, and they have an external notch between them, and this point P. That is to say, they touch each other externally, and this point P. The center of this circle is here at point O. The center of this circle is here at point M. And the side line that connects their centers together is of course the side line OM. And this side line OM must pass through point P, that is their touching point. Again, the side line OM must pass through their touching point, that is this point P. Or OPM is one side line. Again, OPM, according to this rule 10, OPM is one side line. So we can actually implement rule 10 in our drawing. Why? Because in our drawing we have an external notch between this semicircle and this quarter circle at point S. The center of this semicircle is here at point O. The center of this quarter circle is here at point C. And the side line that connects their centers together is of course the side line OC. And this side line OC, according to rule 10, must pass through their touching point, that is point S. Again, the side line OC must pass through point S, that is their touching point. Or OSC is one side line. Again, OSC is one side line according to rule 10. So we join points OSC together by side line, and according to rule 10, the side line OC must pass for point S, that is their touching point. So from the drawing it is very easy to see that the side line OC passes for point S, and that is their touching point. So if OSC is one side line, it means that OC must be equal to OS plus SC. Again, OC must be equal to OS plus SC according to rule 10. So I write it down. OC equals to OS plus SC. So OC equals to OS. OS is the radius of this semicircle that equals to x over 2 units in its length, plus SC. SC is the radius of this quarter circle that equals to x according to our definition. So in conclusion, we found out that OC equals to OS, that is x over 2, plus SC, that is x. So in total, OC equals to x over 2 plus x, that is 1.5x, or 3 over 2 times x. So OC equals to 3 over 2 times x units in its length. This is 97 OC, that is equals to 3 over 2 times x units in its length. In the next step, I'll copy the right triangle ODC in the new page, and we will implement the Pythagoras theorem on this right triangle ODC. Side OD equals to x over 2 units in its length. Side DC equals to 5 units in its length. And we just right now found out that the hypotenuse OC equals to 3 over 2 times x units in its length. Here by PT is the solution for Pythagoras theorem. So actually, this is the right triangle ODC that is coming from the original drawing. This right triangle ODC, according to the Pythagoras theorem, OC square equals to OD square plus DC square. So I write it down. OC square, that is the square of the hypotenuse, equals to OD square plus DC square. OC equals to 3 over 2 times x units in its length, therefore OC square will be equal to 9 over 4 times x square. 9 over 4 times x square, and it is equals to OD square. OD is x over 2, therefore OD square is x square over 4. Plus DC square. DC is 5, therefore DC square is 5 square, that is 25. So if we found out that 9 quarters times x square equals to 1 quarter x square plus 25. Here we subtract x square over 4 from this equation, and we get that 9 quarters x square minus 1 quarter x square equals to 8 quarters x square, and it is equals to x square over 4 minus x square over 4 is 0, so we left only with 25. And we found out that 8 quarters x square equals to 25. 8 over 4 is 2, so this expression equals to 2x squared, and 2x squared equals to 25. Here we divide this equation by 2 and finally get that x squared equals to 25 over 2. So here we take a root out of this equation and finally we get that x equals to the square root of 25, that is 5, over square root of 2. So in conclusion, we found out that x squared equals to 25 over 2 and x equals to 5 over square root of 2 units in its length. Our mission is to find out the area of this green shape. So what is the area of the green shape? From the drawing, it is very easy to see that the area of this green shape equals to the area of rectangle ABCD minus the area of this semicircle minus the area of the quarter circle. Again, the area of the green shape equals to the area of rectangle ABCD minus the area of this semicircle minus the area of this quarter circle. So I write it down. The area of the green shape equals to the area of rectangle ABCD minus the area of the semicircle minus the area of the quarter circle. So what is the area of rectangle ABCD? We know that the area of a rectangle equals to the length of the rectangle times the width. The length of rectangle ABCD is AB, that is 5, times the width. The width is BC, that is x. So in total, the area of rectangle ABCD equals to 5x. Minus the area of the semicircle. So what is the area of this semicircle? We know that the radius of this semicircle equals to x over 2, and therefore the area of any semicircle is pi times the radius square over 2. So, and the area of this semicircle, will be equal to pi times x over 2 squared, that is the radius squared, over 2. So I write it down. The area of the semicircle equals to pi times the radius squared, that is x squared over 2 divided by 2, minus the area of the quarter circle. Minus the what is the area of this quarter circle? We know that the radius of this quarter circle is x. Therefore, the area of this quarter circle must be equal to pi x squared over 4. So the area of the semicircle equals to 5x. Here we have minus pi over 2, and x squared over 2 is x squared over 4. X over 2 squared is x squared over 4. So in total, this expression equals to pi x squared over 2 times 4, and here minus pi x squared over 4. So the area of the semicircle equals to 5x. Here we have in the denominator 2 times 4, that is 8. So in total, this expression will be equal to minus pi x squared over 8. And here we have minus pi x squared over 4. So here we multiply both the numerator and the denominator of this expression by 2 in order to have a common factor with this expression. And the result will be here minus 2 pi x squared over 8. So the area of the semicircle equals to 5x, and here we have minus pi x squared over 8 minus 2 pi x squared over 8 is minus 3 pi x squared over 8. So in conclusion, we found out that the area of the green shape equals to 5x minus 3 pi over 8 times x squared. But we have already found out that x squared equals to 5 over square root of 2, x squared equals to 25 over 2, and x equals to 5 over square root of 2. So therefore we can substitute x in this expression by 5 over square root of 2, and x squared by 25 over 2. We'll do it now, and we'll get that the area of the green shape equals to 5x, and x is 5 over square root of 2 minus 3 pi over 8 times x squared, and x squared is 25 over 2. So there the green shape equals to, here we have 5 times 5 is 25, so in total this expression equals to 25 over square root of 2. And here we have minus 3 pi times 25 is equal to 75 pi divided by 8 times 2, that is 16. So in total we found out that the area of the green shape equals to 25 over 2 square root of 2 minus 75 pi over 16 square units, and the value of this expression is actually equals to 2.95 square units. Repeat again, we found out that the area of this green shape equals to 2.95 square units. We finished with the second question. In the next step, I will summarize the lecture. We start with the first question, of course. Our mission in the first question is to find out the area of the semicircle that is inside quarter circle A or B. So in the drawing we have quarter circle A or B. We know that side AO equals to 5 units in its length. That is to say the radius of this quarter circle equals to 5 units. And inside this quarter circle A or B we have this semicircle, and our mission is to find out the area of the semicircle. Okay, so first of all, we defined the center of this semicircle. This point is point O. We define the touching point between the semicircle and the quarter circle. This point is point F. We define the second touching point between the semicircle and the quarter circle. This point is point G. Likewise, we define the point of tendency of tangent BO. In this semicircle, this point is point L. And finally, we define the point of tendency of tangent AO with this semicircle. This point is point H. In addition, I actually defined the radius of this semicircle as x. So CF, that is the radius of this semicircle, equals to x, and CG is also the radius of this semicircle, that is equals to x according to our definition. In the next step, we join point C and F together by straight line, and point C and H together by straight line. CH is the radius of the quarter circle, that is equal to x, and CL is also the radius of the quarter circle, that is equal to x. So here we can implement rule 1. Why? Because we have the radius CL that is equal to x. The radius CL is drawn to point L, that is the point of tendency of tangent BO with this semicircle. Whenever you have a radius that is drawn to the point of tendency, then tangent BO will be perpendicular to the radius LC. If BO is perpendicular to LC, it means that this angle equals to 90 degrees, and this angle also equals to 90 degrees according to rule 1. Likewise, we have here the radius CL, there's radius CH that is drawn to point H, that is the point of tendency of tangent AO with this semicircle. And whenever you have a radius that is drawn to the point of tendency, then tangent AO will be perpendicular to the radius HC. If AO is perpendicular to HC, it means that this angle equals to 90 degrees, and this angle also equals to 90 degrees according to rule 1. By doing these constructions, we get a quadrilateral CHOL. Inside quadrilateral CHOL, we have 1, 2, 3 right angles. The sum of 3 right angles is 270 degrees, so 270 degrees plus the size of this 4-piece angle, in total it must be equal to 360 degrees, according to the rule that says that the sum of the angles in any quadrilateral is equal to 360 degrees. And therefore this 4-piece angle must be equal to 90 degrees in its size. So inside quadrilateral CHOL, we have 4 right angles. And according to rule 5, any quadrilateral that has 4 right angles must be at least right angle, if not a square. So we write to quadrilateral CHOL is right angle because it has 4 right angles. But we also know that the opposite sides of right angle are equal to each other. So in right angle CHOL, side CH must be equal to the opposite side OL. But CH is x, therefore OL must be also equal to x. Likewise, according to the sum rule, in the sum rectangle CHOL, side CL must be equal to the opposite side OH. But CL is x, therefore OH must be also equal to x. So if we found out that quadrilateral CHOL is not a rectangle but a square, why? Because of the fact that all of its sides are equal to each other. Okay, so in the next step we join points O and C together by straight line. By joining points O and C, we can do the right and associated triangle, triangle CLO. So copy this triangle CLO in a new page and we implemented the Pythagoras theorem on this right and associated triangle, triangle CLO. So actually, this is the right and associated triangle, triangle. This is the right and associated triangle, triangle CLO that are going from the original drawing. According to the Pythagoras theorem, in any right triangle, the square of the hypotenuse equals to the sum of the squares of the perpendiculars. The hypotenuse in this right triangle CLO is CO, and therefore the square of the hypotenuse is CO squared, and CO squared must be equal to CL squared plus LO squared. CO is the missing side, so we leave it as it is, so CO squared equals to CL squared. CL is x, therefore CL squared is x squared, plus LO squared. LO is x, therefore LO squared is x squared. So in total, we found out that CO squared equals to x squared plus x squared. X squared plus x squared is 2x squared. So we found out that CO squared equals to 2x squared. Here we took out all of this equation and finally found out that CO equals to the square root of 2 times x units in its name. So actually, this is 97 CO that equals to square root of 2 times x units in its name. In the next step, we join points O and F together by straight line. OF is the radius of the quarter circle that is equals to x that is equals to 5 according to what is given as the question. So here, so OF equals to 5. We have this is the center of the quarter circle. This is point O, that is the center of the quarter circle. So from the center of the quarter circle, that is to say from this point O, we have line segment OC that bisects chord FG. Again, from the center of the quarter circle, that is to say from this point O, we have here line segment OC that bisects chord FG. That is to say, line segment OC divides chord FG into two halves. Each half equals to x. CF equals to x and CG equals to x. And therefore, we can implement here rule 7. So I can quickly on rule 7. According to rule 7, if a line segment that is drawn from the center of the circle bisects the chord, then the line segment is also perpendicular to that chord. So in the drawing we have a circle, and this is point O, that is the center of the circle. So from this point O, we have here line segment OM that bisects chord AB. That is to say MA equals to MB. And because of the fact that line segment OM that is drawn from the center of the circle, that is to say from point O bisects chord AB, therefore line segment OM will be also perpendicular to chord AB. If OM is perpendicular to AB, it means that this angle equals to 90 degrees and this angle also equals to 90 degrees according to this rule, rule 7. So whenever you have a line segment that is drawn from the center of the circle and bisects a chord, then that line segment will be also perpendicular to that chord. So we can implement rule 7 in our drawing. Why? Because in our drawing, point O is the center of the quarter circle. So from the center of the quarter circle, that is to say, from point O, we have line segment OC that bisects chord FG. So all the requirements of rule 7 are satisfied, and therefore according to rule 7, line segment OC will be also perpendicular to chord FG. If OC is perpendicular to FG, it means that this angle equals to 90 degrees and this angle also equals to 90 degrees according to rule 7. In the next step, I copied the right and green triangle CFO in a new page and we implemented the Pythagoras theorem in this right triangle CFO. This is the right triangle CFO that are going from the original drawing. The hypotenuse FO equals to 5, CF equals to x, and CO equals to the square root of 2 times x units in its name. According to the Pythagoras theorem, in this right triangle CFO, FO square equals to FC square plus CO square. Again, FO square equals to FC square plus CO square. FO is 5, therefore FO squared is 5 squared, that is 25. And it is equals to FC squared. FC is x, therefore FC squared is x squared plus CO squared. CO is equal to 2 times x, therefore CO squared is 2x squared. So in total we found out that 25 equals to x squared plus 2x squared. X squared plus 2x squared is 3x squared. So we found out that 25 equals to 3x squared. Here we divided this equation by 3 and finally found out that x squared equals to 25 over 3. Our mission is to find out the area of this semicircle. We know that the radius of this semicircle is x, and therefore the area must be equal to pi times the radius squared over 2. So it will be equal to pi times the radius, that is x squared over 2. So the area of the semicircle equals to pi x squared over 2. So it is pi over 2 times x squared. And we just found out that x squared equals to 25 over 3, therefore we can substitute x squared in this equation by 25 over 3. We did it and we found out that the area of the semicircle equals to pi over 3 times x squared. And x squared is 25 over 3. So in total, the area of the semicircle equals to 25 pi over 2 times 3, that is 6. So it is 25 pi over 6 square units. In terms of numbers, the area of this semicircle equals to 13.09 square units. We finished with the first question. In the next step, I actually presented to you the second question, and we solved the second question. Our mission in the second question is to find out the area of this grand shape. So in the drawing we have rectangle ABCD. We know that side AB of this rectangle ABCD equals to 5 units in its length. In addition, inside this rectangle ABCD we have this semicircle and this quarter circle. Again, our mission is to find out the area of this grand shape. So first of all, we defined the radius of this quarter circle as x. That is to say, BC, that is the radius of the quarter circle, equals to x according to our definition. We know that all the angles in any rectangle are right angles. Therefore, this angle is a right angle. In addition, we know that the opposite sides of a rectangle are equal to each other. So in rectangle ABCD, side AB must be equal to the opposite side DC. But AB is 5, therefore DC must be also equal to 5 units in its length. Likewise, according to the sum rule in the sum rectangle ABCD, side BC must be equal to the opposite side AD. But BC is x, therefore AD must be also equal to x. We define the center of this semicircle, this point is point O. So we know that AD equals to x. AD is one side of rectangle ABCD, but AD is also the diameter of this semicircle. So we know that the diameter of this semicircle AD equals to x. If the diameter AD equals to x, the radius must be equal to half of it. So the radius must be equal to x over 2. So the radius OA of this semicircle equals to x over 2 units in its length. And the radius OD of this semicircle is also equals to x over 2 units in its length. Okay, so in the drawing, we have an external length between this semicircle and this quarter circle. That is to say, they touch each other externally at this point, point S. And whenever we have an external length between two circles or semicircles or quarter circles, you can implement Rule 10. So I'll pitch quickly on Rule 10. According to Rule 10, if two circles touch each other externally, then the straight line that connects their centers together passes through their touching points. So in the drawing we have two circles, and they have an external length between them at this point, point P. That is to say, they touch each other externally at this point, point P. The center of this circle is here at point O. The center of this circle is here at point M. And the straight line that connects the circles together is of course a straight line OM. So this straight line OM must pass through their touching point, that is point P. Again, the straight line OM must pass through point P, that is their touching point, according to Rule 10. Or OPM is one straight line. Again, according to this Rule 10, OPM is one straight line. So we can implement Rule 10 in our drawing. Why? Because in our drawing, we have an external between this semicircle and this quarter circle. That is to say, they touch each other external in point S. Therefore, can implement here rule 10. The center of this semicircle is at point O. The center of this quarter circle is at point C. And the straight line that connects the centers together is of course the straight line OC. So this straight line OC must pass for point S, that is the touching point. Again, the straight line OC must pass for the touching point, that is point S. Or OSC is one straight line. Again, OSC is one straight line according to rule 10. But if OSC is one straight line, it means that OC must be equal to OS plus SC. Again, OC equals to OS plus SC. So OC equals to OS. OS is the radius of this semicircle, that is equals to x over 2, plus SC. SC is the radius of this quarter circle, that is equals to x. So in total, OC equals to OS, that is x over 2, plus SC, that is x. So in total, OC equals to x over 2 plus x, that is either 1.5x or 3 over 2x units in its length. So OC, the opponent OC is equals to 3 over 2 times x units in its length. In the next step, I actually copied the right triangle ODC in a new page and implemented the Pythagoras theorem of this right triangle ODC. So actually, this is the right triangle ODC that are going to the range of domain. We just right now found out that the hypotenuse OC equals to 3 over 2 times x units in its length, OD equals to x over 2, and DC equals to 5. So according to the Pythagoras theorem, in this right triangle ODC, OC squared, that is the square of the hypotenuse, must be equal to OD squared plus DC squared. Okay, so OC is 3 over 2 times x units in its length, therefore OC squared is 3 over 2 times x squared, that is actually 9 quarters times x squared, and this equals to OD squared. OD is x over 2, therefore OD squared is x squared over 4 plus DC squared. This is 5, therefore DC squared is 5 squared, that is 25. So in total, we found out that 9 quarters x squared equals to 1 quarter x squared plus 25. Here we subtracted x squared over 4 from this equation, and finally found out that 9 quarters x squared minus 1 quarter x squared equals to 8 quarters x squared, and this equals to 25. So 8 over 4 is 2, so in total this expression equals to 2x squared, and 2x squared equals to 25. Again, 2x squared equals to 25. Here we divided this equation by 2 and finally found out that x squared equals to 25 over 2. So here we took a root out of this equation and finally found out that x equals to the square root of 25, that is 5, over square root of 2. Our mission is to find out the area of this green shape. So what is the area of the green shape? From the drawing, it is very easy to see that the area of this green shape equals to the area of rectangle in the CD minus the area of the semicircle minus the area of the quarter circle. Okay, again, the area of the green shape equals to the area of rectangle in the CD minus the area of the semicircle minus the area of the quarter circle. So what is the area? Of this rectangle? Rectangle in the CD. The area of a rectangle equals to the length of the rectangle times the width. The length of rectangle ABCD is AB, that is 5, times the width. The width is BC, that is x. So in total, the area of rectangle ABCD equals to 5x. And the area of rectangle ABCD equals to 5x minus the area of the semicircle. The area of any semicircle equals to pi times the radius of the semicircle squared, and divided by 2, of course. Again, the area of any semicircle equals to pi times the radius of the semicircle squared divided by 2. And therefore, the area of the semicircle must be equal to pi times x over 2 squared divided by 2. Repeat again, the area of the semicircle is equals to pi times the radius squared, that is x over 2 squared divided by 2. Minus the area of this quarter circle. We know that the radius of this quarter circle is x, therefore the area of this quarter circle must be equal to pi x squared over 4. So repeat again, the area of the quarter circle equals to pi x squared over 4. So the area of the green shape equals to 5x, and here we have x over 2 squared is x squared over 4. So in total, this expression is equal to pi times x squared over 4 multiplied by 2. Again, pi x squared over 4 multiplied by 2 minus pi x squared over 4. So the green shape equals to 5x, and here we have pi x squared and 2 times 4 is 8. So in total this expression equals to minus pi x squared over 8. Here we have minus pi x squared over 2. Minus pi x squared over 4. So here we multiply both in the numerator and the denominator of this expression by 2 in order to have a common factor with this expression. So after we multiply it by 2, we get that this expression in total equals to minus 2 pi x squared over 8. So in total the Green shape equals to 5x, and here we have minus pi x squared over 8 minus 2 pi x squared over 8 equals to minus 3 pi x squared over 8. So in total the Green shape equals to 5x minus 3 pi x squared over 8. But we already found out that x squared equals to 25 over 2 and x equals to 5 over square root of 2. Therefore, we can substitute x in this expression by 5 over square root of 2, and we can substitute x in this expression by 25 over 2. We did it, and we actually found out that the Green shape in total equals to 5x, and x is 5 over square root of 2 minus 3 pi over 8 times x squared, and x squared is 25 over 2. So here we have 5 times 5 is 25, so in total this expression equals to 25 over square root of 2. And here we have 3 pi times 25, minus 3 pi times 25 is minus 75 pi, and 8 times 2 is 16. So in total we found out that the Green shape equals to 25 over square root of 2 minus 75 pi over 16 square units. In terms of numbers, the value of this expression is equal to 2.95 square units. Okay, again, we found out that the area of this Green shape equals to 2.95 square units. Okay, thank you very much.